Today we're going to start section 6.3. This section is multiplication and division of rational numbers. And I may have talked about it in section 6.2. I don't remember for sure. The reality is that multiplying and dividing with fractions is easier than adding and subtracting. And in particular, the reason is because when you add and subtract, you have to have those denominators matching. And in multiplication and division, it's irrelevant. So I'd like to start to talk a little bit about how we go about multiplying and then illustrate why that works from a visual perspective. So to start with, multiplication of rational numbers. If a over b and c over d are rational numbers, then a over b times c over d is a times c over b times d. It's what we wish were true with addition and subtraction, right? Man, do we wish it. Multiply across, multiply across. Now, as you work with problems like these, sometimes you don't actually go through it quite like this. Sometimes you reduce things along the way. You don't have to, but it's an option. But in reality, you could just multiply across the top, multiply across the bottom, reduce at the end. All right, so I'd like to show you a rectangular region diagram to illustrate why this works. So to start with, just draw yourself a rectangle. Imagine that it's a cake. And I hope you're not hungry. All right, so what I'd like for you to do is I'd like for you to split it vertically into 5 columns. They should all be the same width. I'm sure that mine won't be, and you'll forgive me and I'll forgive you. It'll all be good. Something like that. So imagine you made the birthday cake and you split it into 5 columns, right? And brothers and sisters and mom and dad and roommates and whoever you live with came in and they eat part of the cake. And so the reality is that part of it is now gone. In fact, only 3/5 of it remain. So you really only have 3 of these columns that are still here. Okay, so that's the amount of cake that's actually left, 3/5. So then you take that 3/5 to your whatever's next. Maybe it's your youth group or your Bible study or something, and there's only 3/5, right? It's not a whole cake. It's just 3/5 of a cake. But of course, there was other divisions that were made in this cake, right? I mean, you did it vertically and horizontally when you really did it. So I'd like for you to visually then divide the cake into 4ths horizontally. Again, they should be equal. Mine absolutely are not, but pretend. So I mean, we could count, right? So your parents at home, whoever you met, they ate 4 of the pieces, if you want to think about it that way, right? They ate 4 of them. There's only 12 of them left. I mean, there's lots of things we could count from this diagram. I want you to focus just on the yellow pieces, though, because those are the pieces that are still in your cake, just the yellow, okay? And now I want you to think about taking those yellow pieces and thinking about them horizontally now instead of vertically. And I want you to shade in 3/4 of what's there. So I'm going to change the color that I'm working with to blue. So I'm going to have 3 rows that I'm talking about. So thinking only about the yellow that remains, split horizontally now instead of vertically. 3/4 when I leave the Bible study, the youth group, whatever, remains. And the question is, this sort of double shaded region, how much of the original cake did we actually have left over? And we can count. So how many of my boxes are, in essence, double shaded? 9 of them. Okay, 9 pieces remain. But how many pieces were in the original cake? 20. And if you go back up and you look at the values themselves, this is really multiplying across the top and multiplying across the bottom to get the 9 out of 20. And obviously that's just one illustration, but it gives you some kind of an idea of why this idea of multiplying works so well and works at all. Identities and inverses. The multiplicative identity, which those of you who've had number theory, we ran into the identity idea back in chapter 3, I think. 1 is the unique value. It's very special. It has this property that when you multiply with it, it doesn't change anything. So if I multiply by the number 1 by a over b or by a over b in the other order, I still end up with a over b. And oftentimes when we think about it, we kind of feel like, well, that's rather useless. If I multiply by something and it doesn't change anything, what's the point? Well, it actually has a lot of value, and you just used it to a great extent in section 6.2. The reason that it's okay to multiply the top and the bottom by the same number 2 or 7 or whatever is because 2 over 2 or 7 over 7 is equal to 1. So in fact, it changes it in how it looks, but it doesn't change the actual value you're working with. So this is a very valuable property. The multiplicative inverse property, some people talk about it being a flip of a fraction or the reciprocal of a fraction. So for any non-zero rational number, a over b, then b over a is the unique number such that when you multiply it, you get back to the multiplicative identity 1. And this has immense power when you're solving equations, right? You're trying to isolate a variable, you're trying to move a fraction or even just a whole number, if you think about it in fractional sense, to the other side, to get it away from your variable, we use multiplicative inverses. Now there are a few other properties for multiplication. These two are very important. The others are sort of grouped together. 611, Theorem 611. So the first one is the distributive property. The distributive property of multiplication over addition says if you have a over b, c over d, e over f rational numbers, and you're multiplying with them, that it works just like it did with whole numbers and integers. I can multiply across the addition sign or through the parentheses, and I end up getting that the a over b is multiplied by the c over d, and the a over b is multiplied by the e over f, and then they're combined with addition when they're done. Another very useful property when working with equations is the next one, the multiplication property of equality. The multiplication property of equality talks about what we're allowed to do across two sides of an equal sign, and we had this property again back in chapter 3, if you've taken number theory. It says that I'm allowed to multiply by the same thing on both sides of an equation, and again, it's a valid operation. It works. It doesn't change any part of it and make it not equal to one another. So a over b equals c over d. If you have two fractions in this case, or rational numbers that are equal, just different versions of each other, right? Like 1 over 2 and 2 over 4 or something like that. Then if I multiply both of them by some other number, the same number, they're still going to be equal to each other when I'm done. And we use that all the time when we're solving equations. The third one inside of 611 talks about what happens when you do the same thing but with inequalities. There's some left over from before. So if I have fractions a over b, c over d, e over f, and we have the relationship where a over b is larger than c over d, and this number e over f is positive, then if I multiply it on both sides, the direction of the inequality stays the same. I still end up with a over b, and it's what it's been multiplied by, greater than the c over d, right? In particular, what you notice is that the sign stays. But it only works because this is positive. Right? I'm multiplying by a positive number on both sides. So the only difference on part 2 of this theorem, or this portion of the theorem, is that instead of multiplying by a positive, now we're multiplying by a negative, right? E over f less than 0 means it's negative. And when you multiply by a negative number, the direction of the inequality changes. It was greater than, and now it's less than. And I'll just do an example with whole numbers because it's cleaner and easier to see, but not any less accurate. So for instance, if I had -5 less than 4, and they don't have to be positives or negative, but this works, right? -5 is less than 4, agree? Sure. And if I multiply by a negative on both sides, so let's say I multiply by -2. So -2 times -5 is 10. 4 times -2 is -8, and 10 is greater than -8. So the direction of the inequality changes, and it works any time that you multiply by a negative. Okay? And the last theorem, or last portion of 611 theorem, talks about what happens when you multiply by 0, because that's the only other option. We've talked about positives, we talked about negatives, what happens when we talk about zeros. So if a over b is a rational number and you multiply by 0, you get 0. It's a 0 property of multiplication, also in chapter 3. So if you were to go back, if you have seen some of these properties before, and look at chapter 3 that I keep referencing, the only property on this front page of your notes that's any different than you had before is the inverse property. We didn't have inverses before because we didn't have fractions, so there's no ability to flip things upside down. It's the only new property that exists. All right, so we are going to use some of these properties and solve an equation. And as we solve this, we're trying to identify what property we're using. And sometimes it's a little trickier than it might actually first appear because you're so used to being able to just use them and not think about why what you're doing works. So taking a look at 3 over 4x equals 1 over 5. And our goal is to solve for x. What would I do to solve for x in this problem? Okay, so we could divide both sides by 3/4. Is there another way of representing that? Good. It's kind of funny when we multiply and divide with fractions because dividing by fractions feels a little bit tricky. So it's sometimes easier to think about it as multiplication with the reciprocal. So I'm going to represent it as multiplication with the reciprocal. Now, already I've used a property of multiplication. Can you look back at your list of properties and figure out what in the world property did I use when that's the only thing I've written down so far? Not yet. We'll use that in a minute. You're real close. Something else we've used. This is the multiplication property of equality. The fact that I'm allowed to multiply both sides by the same thing and it doesn't change its equalityness, its equalness, is a property of equality. Now, our basic idea of why we chose 3 over 4 or 4 over 3, that part of it has to do with the identity, right? With the inverse, rather. So we're about to do that, and we will actually see that happening. So this piece right here actually equals, what is 4/3 times 3/4? That is 1x. So as I multiplied that, that's actually the inverse property. The fact that when I multiplied by this very specific value, I ended up getting back the identity 1. And then 1/5 times 4/3 would be 4 over 15, right? Sure. Okay, now my goal is to get x alone, and it kind of sort of is. Because what's 1 times x? It's really x, right? But there's a property that actually says that that's true. What property says that 1 times x is equal to x? That's the multiplicative identity property. I'll call it ID. So do you see what I mean? You almost look at this problem and you're like, it's a one-step problem. But there are 3 properties of equality that we had to use to actually make that work. We had to use the multiplication property of equality, the inverse property, and the identity property to actually see all those pieces come into play the way we wanted them to. Okay, example 3, same idea. It's just that it's messier to work with. And there's more ways to do the problem. So we'll do it together, and you guys are going to lead the discussion of the how. So taking a look at this problem, 2x over 3 plus 1/4 equals x over 6 minus 1/2. There's lots of ways that we could do this problem. So somebody give me a suggestion of what you might want to do first, and then we'll work on why we can justify allowing it to happen. Okay, so Danielle says she would like to add the 1/2 to both sides. Okay, so that's actually a property that we encountered back in section 6.2. Any idea what that one is? Why we're allowed to do that? It is. It's the addition property of equality. Okay, fantastic. So now I have 2x over 3, and I have x over 6 on the right. What am I going to do with 1/4 and 1/2? Okay, and how will we add them? I'm going to shift this over to space. Okay, get a common denominator. So what in the world would my common denominator need to be to make that work? Yeah, 4 will work, 8 will work. 4 is a little bit smaller to work with, so I'll go with 4. So if I do 1/4 and 2/4, right, then I have 2x over 3 plus 3/4 equals x over 6. And the combining the common denominators, all that kind of stuff is actually, again, from section 6.2. This is the theorem of addition of fractions. Okay, what do you want to do next? Okay, so we can subtract 2x over 3 from both sides, I assume, yes? Okay, so that's like the same thing we just did before in terms of like what property allowed it, right? It's the addition property of equality. So you might feel like, well, didn't I subtract? Yes, you subtracted or you added a negative, so it's still an addition property. If you want to write subtraction property, you're not going to hurt my feelings, it's okay. Addition property of equality. All right, so I have 3/4 on the left. And right now I have x over 6 minus 2x over 3. So what am I going to do with that next? Yeah, common denominator again. So it's friendly enough to multiply the denominator and the numerator by 2 here, right? And inherent in doing so, I didn't write this down before, so I will write this down here. This is the theorem of addition, right, again. And it is, but the reason that I'm allowed to multiply by the 2 over 2, which I did in twice, I did it back on step 2 and on step 4, the reason I'm allowed to do that is because this is actually the multiplicative identity, isn't it? Right? The reason I'm allowed to multiply by 2 over 2 is because it's really just 1, and multiplying by 1 doesn't change anything. So that's actually what's going on sort of behind the scenes. I've got the multiplicative identity property. So let's do that part. I have 3/4 on the left equals, let's see, x over 6 minus 4x over 6, which gives me what? Negative 3x over 6, and we could actually reduce that, like you said, which is negative x over 2. So, and believe it or not, even at this point, when we are reducing is actually a multiplicative identity as well, because we're dividing the top and the bottom by the same value, hence multiplying it by the same value is reciprocal. So this is another multiplicative identity property here. 3/4 over equals negative x over 2. Now what? I don't think we want to divide by 2. We're close. Multiply by, somebody said negative 2. That's a great plan. So if we multiply by negative 2, what we end up having on the right-hand side is that this negative 2 and this negative 2, they multiply to give me the value of 1, really, correct? So this gives me 1x on the right, and that is, I think I'm on step 5, kind of. The multiplicative property of equality allows me to do the multiplication, and it's the multiplicative inverse that's giving me the number 1. Both of those are at play in that one. What do I get on the left-hand side? negative 6 over 4, right, because this is negative 2 over 1. All right, so this is negative 3 halves. And I've got x. So again, on the right-hand side, this is the multiplicative identity, because 1 times x is x. And on the left-hand side, right, the left-hand side is actually the multiplicative identity, because I'm dividing by 2 on the top and the bottom as well. Multiplying, dividing, they're the same thing, just from a different perspective. And we're done, right? It's really taxing to write out all those steps, isn't it? It really is. There is a lot going on when we work with fractions and solving equations. All right, let's shift gears and talk just for a little while before we end our class about division. We'll see how far we get. Division of rational numbers. Because I keep telling you that division and multiplication they're kind of the same thing. I should probably justify that and not just say it, right? So to start with, if we have a over b and c over d, rational numbers, and we want to divide a over b divided by c over d, and it's equal to something, and we're calling it e over f, then that will be only true if, or it will be true if and only if e over f is a unique rational number such that c over d times e over f is equal to a over b. So write that in, and then I'll again justify with some whole numbers just because it's easier to see it working. I don't want 5. So let's talk about 6 divided by 2. What's 6 divided by 2? 3. Why? Well, the real reason why is because 2 times 3 equals 6. And that's what this is saying down here. The reason it really works, the reason it has that answer is because if you multiply it by the other side, the two values are going to be the same. Okay? So this is why it's so important for kids to learn their multiplication facts, in spite of whether their calculator can be used or not. Because if they have to try and skip count every single time to get their multiplication facts, division becomes really, really hard. Multiplication facts are super important. I have had to go back with one of my 11-year-olds and redo multiplication facts twice because they forget. And she keeps forgetting them, and then division becomes really, really hard. All right, I'd like to show you an algorithm for the division of fractions and talk about why it works. So the algorithm for division of fractions says the following. If you have a over b and c over d and you're trying to divide them, a over b divided by c over d, then a over b is going to be multiplied by the reciprocal d over c. I can't remember the cutesy little saying that's absolutely horrible from a teaching perspective, but it says something like, yours is not to reason why, simply flip and then you divide. I can't remember how it goes exactly. It's terrible. It's definitely something you should know why. You should never just say, it's just the way it is because it is. Kids don't like that. You guys don't like that. If I were to tell you that, you'd be like, I don't think she really knows the answer. Wouldn't you? And your students will do it too. So whether or not a student does this initially to you at some point and you forget how to do it or whatever, coming back to a student and saying this is why it works is always valuable because it validates that you know what you're talking about. That's really what it does. So I'd like to show you why this really works. Why in the world we can simply change the division into multiplication and flip the fraction and it actually makes sense. So let me show you. So let's say we have it starting out exactly like it describes, a over b divided by c over d. Okay, so far so good? Okay, so now earlier, I think it was Bailey, Bailey had talked about when we were solving equations, dividing by a fraction, and I was like, oh, it looks so messy, right? That's kind of why I said, let's do the multiplication by the reciprocal part instead, and it works so much prettier. So the reality is, because this is what happens when you divide by a fraction. A over b divided by c over d. And you get fractions inside of fractions, and none of us really like that, right? That's gross. It just looks awful. But bear with me for a moment, because it's going to prove to us that this actually works. That's what it means to do division, right? I'm dividing a fraction by a fraction, and this is another way of viewing it. All right, but we know that we have this property that allows us to multiply the numerator and the denominator by the same value, and it works, right? We know we have that property. So what I'm going to multiply the numerator and the denominator by is the reciprocal of the denominator, c over d. And I'm allowed to multiply by anything as long as it's not 0. And none of these numbers were 0 to start with because they actually were defined that way. The c over d numbers themselves, right? It doesn't work. So no zeros in there. I wrote that upside down on top. I'm sorry. I was supposed to say d over c. Please fix that if you were copying what I had. D over c. So I multiply by d over c on the top. I multiply by d over c on the bottom. Totally valid because d over c divided by d over c is what? 1. Okay, so I'm allowed to do that. The beautiful thing, of course, in the denominator is that when I did that, what is c over d times d over c? It's 1, right? So in the numerator, I get a over b times d over c. In the denominator, I get the number 1. And what is anything divided by 1? Itself. So I end up with exactly what I was proclaiming to be the case, that I'm allowed to flip the fraction, the second fraction, upside down and make it multiplication instead of division. Okay, I think I have time to do the example 4 and 5 to see how this works real quick. All right, this says to describe what is meant by 6 divided by 2 and to show a diagram to support your description. And there's a couple of ways to do this, but one is helpful when referencing fractions, and the other one is really not that helpful for fractions specifically. So I'm going to show you the one that's helpful for thinking about in terms of fractions, because that's what we're working with, right? So the idea is to break 6 into groups of size 2. So imagine having, and you can draw them, 6 cookies. Oh, wow, that's not good. Let's copy paste. I don't really know what flavor these are because they're purple, but blueberry cheesecake, how's that? Y'all good with that? Blueberry cheesecake cookies? Okay, so I have 6 cookies. And what I'm going to do is I'm going to break these 6 cookies apart into groups of 2. So this is one way, and this gives me 3 groups. Right? 6 divided by 2 is 3, for sure. I have broken the number 6 apart into 3 groups of 2. So thinking along that idea, we can actually do the same thing for 6 divided by 1/2. So let's do our same 6 cookies that we had before. That wasn't what I wanted to do. And we're going to break 6 apart into groups of size 1/2. What's that mean? It means I need to cut my cookies in half, doesn't it? So imagine you had like the cookies for, City Bites over there. We got a City Bites. Are you guys excited about that? You should be. I love City Bites just for that reason alone. All right, so now I've got groups of size 1/2. How many groups of size 1/2 do I end up having? There are 12 groups, right? So the 6 divided by 1/2 sure enough, became 6 times 2 over 1, which was, in fact, the 12. And that's a visual to show how that works from that perspective. All right, we will finish up this section with exponents next time.